Hello, and welcome to US 275 Scientific Ethics, where today we're going to think about, actually talk about thinking and acting as a scientist. And so hopefully coming out of the last set of lectures, you've got an idea what science is and potentially what science is not. And now I want you to think about, how it is that scientists look about the world around us. And, as much as people may hate to admit it, how a lot of the things that you do in your daily lives, kind of regardless of your major, you don't have to be a science major to do this, but ways in which you're going to be using the scientific method and thinking and acting as a scientist as you go through your life without even thinking about it. So to start out with, I want you to think about how do children learn about the world? So this is an old picture of my oldest son many, many years ago. But basically, what happens to a child as they're kind of growing up, especially in those kind of toddler years, when they're, trying to figure out, what's going on in the world around them and try to figure out their explanation, figure out, what is allowed, what is not allowed, because for toddlers, that's an important thing to them. So what they do is they're going to observe the situation and they're going to try to come up with a set of rules. What am I allowed to do? What am I not allowed to do? What do I get away with? What do I get in trouble with? And they're going to take those new rules, and especially if you've got younger siblings or perhaps children of your own, that kids are great at kind of figuring out what the rules are, but then kind of testing those rules and trying to figure out where the boundaries of the rules are, where are the limits to the rules. How do these rules apply in new situations? And so basically what they're going to do is they're going to test it. They're going to test the rules. They're going to test the parents. They're going to test, and say, okay, what is my explanation, and how well is it at predicting what I'm going to get in trouble with, or what I'm going to get away with in the future? And so you see the kids kind of going through and doing this, and they're continually kind of testing the rules and continually asking, do the rules as I understand them work? And if the answer is yes, their explanation is still maintained and they keep the rules and they keep doing what it is that they're doing, but they're still going to continue to test that. But if it's no, it's like, okay, I didn't think I'd get in trouble for this, but now I did get in trouble. So I got to adjust the rules to say, okay, under these circumstances, this is not allowed. So basically, a child going through their early developmental stages are going to be trying to learn about the world and trying to figure out kind of what's allowed and what's not allowed, and kind of what are the rules for dictating what's going on around them. So then we jump forward 20 years or so and say, how do scientists learn about the world? And we say, okay, what do scientists do? They're going to observe situations, going to make an observation of some type of phenomena, and they say, okay, this is interesting. I wonder why this occurred, or I wonder what caused this to occur. And they're going to generalize to form a hypothesis. They're going to come up with an explanation. And then they're going to say, okay, it's a pretty good explanation, but, I know, from the last lectures, or I know from experience that there are lots of different kind of explanations or lots of different hypotheses given a set of data. And so what we want to do is test our explanation, test our hypothesis in a new situation. So the scientists, like the toddler, are going to take their explanation and kind of push around the edges and see, are there limits to these rules? And are there limits to these hypotheses that they talk about? So they're going to do experiments, much like the child is going to test your boundaries, test the rules that they're working with. But the scientist is going to ask, does this hypothesis work? Does this hypothesis predict my observation based on this experimental condition or that experimental condition? And if it's yes, you keep the hypothesis and you continue testing it. If it's no, then you say, okay, the rules didn't work under this circumstance. My explanation wasn't good enough. And so we got to take a look at it and come up with an alternative explanation. We kind of come up with an explanation that's even better than the one we had before, even better at predicting, what we're going to see the next time we do an experiment. And so hopefully what you can see is that the way that children learn about the world is very much similar to the way that scientists learn about the world. We just use different terms for what it is that we're doing, but it's basically kind of a natural kind of instinct, a natural approach to kind of exploring and learning as we're going forward. Now, Albert Einstein, a very famous physicist, says imagination is more important than knowledge. The whole of science is nothing more than refinement of everyday thinking. The point that I'm trying to make is that the way that scientists think and learn about the world is very similar to what you do and is very similar to what children do. So, hopefully, not ruining, science for you to say that anybody can do it, but really anybody can do science. Anybody can adapt and then use the scientific method. And going to there, when we think about the scientific method, if you go into a basic science textbook, they're going to tell you, you got to do experiments across, the scientific method, that you got to kind of do something here. You got to identify the problem. You got to gather the data, generate hypothesis, test the hypothesis. Does the new data agree? No. Come up with a new hypothesis. Does the new data agree? Yes. Then you test the hypothesis some more. This is kind of a generic kind of scientific method. And it's, pretty close to what scientists do, but oftentimes scientists take slightly different approaches. But regardless of the approach they take, it's going to be the same basic idea as what the toddler did learning about the world around them. They're going to make an observation of some type of situation, and then based on that situation, they're going to try to figure out what are the rules. They're going to try to find out what caused whatever it is to occur. Remember that cause and effect that we talked about a couple lectures ago. They're going to come up with their explanation, which is going to be the hypothesis. And the hypothesis, as we said before, has to be testable. If it can't be testable, it's no good, because we have to be able to test and say, does it work or doesn't it? So we're going to come up with a testable guess or testable, and when I say guess here, I mean kind of informed guess or informed kind of explanation about the world. So we're not going to come up with really outlandish things. We're going to base it on what we've learned previously, based on the work of others, but we're going to come up with this explanation about how the world works around us. Based on that testable guess about how the world works, we're going to predict what's going to happen in the future when we run an experiment under specific situations, specific conditions. And so you run the experiment, you take a look at kind of your guessed prediction about what was going to occur and put that in relationship to what you actually observe. Was the new data fitting with what you predicted was going to be occurring? If yes, then you do it over again and test it under different conditions, different circumstances, different, whatever. If it's no, then we have to go back and refine our testable guess as to how the world works, make it better, kind of like that sculpture of Michelangelo we talked about previously. Okay, so important is, one of the most important things about science is that hypothesis must be testable. Thomas Hunt Morgan, a famous geneticist that studied fruit flies, Drosophila, about 100 years ago, said, science must disregard all hypotheses that cannot be subject to experimental verification. Basically, can they be tested? Not because they are wrong, but because they're useless. In science, you can have a great explanation, but if you can't test it, you can't come up with a way to figure out whether it's right or wrong, it's no good. It's not science anymore. And so because of that, we have to have a testable hypothesis when we're working in science. When we take a look at that testable hypothesis, we've got to try to figure out a way to do it, because there's going to be lots of different explanations for what's going to be going on. And so William of Ockham, quite a while ago, said pluralitas non est ponenda sine necessitate, which is basically entities must not be multiplied without necessity. And so probably the English version of it doesn't make as much sense as the Latin version. So basically it means that when more than one possibility exists, choose the simplest one. So keep it simple. In general, the simplest explanation is the easiest one to test, and in most circumstances, it's going to be the one that's probably going to be the most accurate. So if we think back to Stonehenge, that giant celestial calendar made up of 100-ton rocks, who built it? It's thousands of years ago, without heavy machinery and all of that. And so we're the builders of Stonehenge, ancient extraterrestrial astronauts or humans. And so we think about that. If it was built by ancient extraterrestrial astronauts, first off, it means that Um, they're extraterrestrials. They're, creatures that are coming from other planets. If they're creatures that came from other planets, they would have to, come to the Earth. So we got creatures from another planet that have traveled around the universe and, stopped by the Earth at some point, 5,000 years ago. And when they came, they were bored and they decided to rearrange some rocks and build a calendar. And so that's complicated. It's based on having extraterrestrials that have the ability to travel through space, that they have the ability to travel to the Earth, that are interested in enough in what's going on in the Earth to study it well enough to be able to understand how the sun and the moon and the stars all, kind of orbit and move around in the night sky. And they've got to be interested enough in building a calendar out of really heavy rocks. So that's, like 5 different things that have to occur in order for ancient extraterrestrial astronauts to have come and built Stonehenge. The alternative explanation is that humans did it for some reason, and we don't know what that reason is. And so even though we don't know how they did it, we don't even know why they did it. It's probably a simpler explanation to say that humans built Stonehenge than ancient extraterrestrial astronauts. And so we, again, want to try to keep it simple and easily testable. It's kind of hard to test, whether humans built it or not, but hopefully if we study it long enough, we're going to be able to find evidence and be able to understand how it is theoretical to build it, similar to how it is we're trying to understand and how the pyramids were built in Egypt. Okay, so science, as we said, is going to be a process of hypothesis testing. We're going to make observations, and based on those observations, we're going to make a hypothesis, an explanation of our observation, and then we're going to test it in some way. So we've got, a couple plants over here, and we're going to say, okay, our hypothesis is that plants that get watered are going to grow better than plants that don't, because plants need water to grow. And so what we're going to do is an experiment. We put 2 little plants together. We put one plant over here that we water. We put one plant over here that we don't water. And lo and behold, the plant with water grows taller. Okay, so it's good evidence that water is important for plant growth. And so that kind of reinforces our hypothesis. If we did the kind of inverse of that and say, okay, we put kind of a natural amount of water on this one over here, and each day we take this plant and we pour water and water and water and water and flood it out. So that this little plant here, this poor little plant here, is basically going to rot. Is going to show us that, water is necessary for growth, but you need the right amount of water. So again, that's a hypothesis that can be tested and gives us a better understanding, at least in this case, about what's necessary for these plants to grow. Another example of this, science is hypothesis testing. If an observation holds true, it supports but does not prove a hypothesis. So we're not coming up with the complete and accurate explanation by simply doing one experiment. We need to test our hypothesis over and over again under lots and lots of different circumstances. And so basically, if it holds it true, it supports our hypothesis but doesn't prove it. If our observations, if our, what we observe when we do the experiment is different from what we expected based on our hypothesis, we then have to revise the hypothesis or develop a new hypothesis. So what this means is basically what Albert Einstein says over here, the case is never closed. So we've got to continually test our explanations in science to make sure they hold up under all the different circumstances. What Einstein says is many experiments may prove me right, again, supporting it here, but it only takes one to prove me wrong. If our observations don't go along with our hypothesis explanations, that means our hypothesis is probably wrong and we're going to have to revise our hypothesis. But regardless of how that occurs, science is going to be advancing because we're going to come up with a better explanation for the world around us. So another example of this, science basically progresses by eliminating wrong hypotheses. So basically a new hypothesis basically has to do everything as well with the old explanation. And so everything that the old hypothesis explained, the new hypothesis has to explain. And it has to explain, where the old hypothesis broke apart, where it didn't work. And so we got to be able to use it for new predictions that can be tested going forward. And therefore, we then have to continually test that new hypothesis until it is eventually falsified and potentially replaced. So when we talk about science, you're often going to hear about scientific laws and scientific theories. And those terms are many times used interchangeably with one another, but they're not exactly the same. A scientific theory is a hypothesis that's been extensively tested and supported. And so because of that, scientific theories are often incorrectly used interchangeably with hypothesis. But a hypothesis is a starting point. If the hypothesis has been tested over and over and over again and holds true, then you can say, it's probably a really good hypothesis, and we can call it a scientific theory. And so example of this is the theory of relativity. And again, we're talking about Albert Einstein a lot today. So E equals mc squared. Energy equals mass times the speed of light squared. Don't worry about it. We're not doing math. You don't have to worry about that at all. So that basically means that Einstein's hypothesis about the relationship between energy and mass has been supported through lots and lots of different experiments. It hasn't been disproved yet, but it works pretty well. In contrast, there are going to be scientific laws, and scientific laws are things that are supported by very extensive experimentation, and in many cases, there are things that can be expressed mathematically. And so you can come up with a formula, you can make your measurements, you can make your observations. They often have other factors that go into them, and you can use that to very accurately predict results under all situations. And so the law of gravity is an example of a scientific law. If you drop an object, it's going to fall towards the earth. And if you're really good at studying it, you're going to see that it falls towards the earth at the same rate of acceleration, no matter where it is, no matter how big it is, all of that. And so there's a mathematical model for how far or how fast an object is going to drop during a period of time. And so again, it's the law of gravity. Gravity, it's not just a good idea, it's the law. So to finish up this lecture, a couple readings, and so we're going to continue on with the text from University of Berkeley. So understanding science, how science really works. This is going to be another set of chapters from what we had on a previous lecture. So what I'd like you to do now is read section 3, how science works, section 4, the core of science, section 7, what has science done for you lately, and 8, a scientific approach to life. And so that's going to finish up the lecture for today. Come back and I'll give you a little bit of insight on the assignment. As always, if you have any questions, feel free to email me. Thank you and have a great day.